Let's start. Grab out a pen or pencil. Let's go in our notes. Here we go. Exercise 9D. Settle down. Thank you. So far, you've learnt, if we had to summarize it, your key skills were first principles, which is theory. You learn first principles first, and then understanding that the whole point of doing first principles was to find the gradient of a tangent line at one point. That was the main idea. The problem with first principles is it takes too long to do, right? And so then there were these rules that essentially were formulated from the first principles, and there are like 7 of them in total, yeah? You had your sine, cos, tan rules. You had your exponential log rules. Then you had power rule, which represents any power function. Power rule, and then combining all that together, you then have chain rule. Friday we'll learn product and quotient. These are all the derivative skills. They're all shortcuts, and they're all applied essentially in place of first principles. So you technically could do first principles for all of these, but these are the rules for those specific functions to find the gradient at one point. That's literally all you're doing. You're just finding the gradient of a tangent line using 1 point. Okay? Today's lesson, we deviate from those skill base, and we're now using the concept of gradients of tangent lines and analyzing how that changes along the function. Here's an example. In exercise 9D, your goal is to look at the graphs of derivative functions. Here's your normal graph. This is your y equals f of x function. We're meant to analyze at every single point on this function, there must be a tangent line that touches that point and has a gradient. Each one has a gradient, so M, 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 that you can map. The M is your derivative. That's your delta y, delta x. Your gradient M could be positive, could be 0, could be negative, and it could be really large negative or really large positive. You're meant to map that. And what would the derivative graph look like if we were just to sketch just the M values? So M could be negative 1 down here, then it becomes negative half, negative something, and then it gets to 0 at some point. What would the graph look like for the derivative of this straight line? That's essentially what you're doing. You're sketching the derivative graph by looking at the graph. Yeah? So, just looking at this, there's infinitely many points. We're going to look at an obvious point here. They gave us 1 and 1, or negative 1 here. That's essentially saying that the gradient for this line has a run of 1 and a rise of 1. Therefore, your gradient at each point, or at this point, should be 1 over 1, which is 1. What's convenient about this is that the gradient for a straight line is consistent throughout. It's the same gradient all the way through. So you can say that at any point on this line, it should be 1, 1, 1, 1, and it's all positive 1. It's a positive gradient. So how do you draw the derivative graph? For every x value that you choose, even if I chose x over here, let's say x is 2, the gradient is 1. So that means when x is 2, gradient is 1. And if you do that for every single point, whether I chose 3, gradient is also 1 again. So at x equals 3, gradient's 1. So what you actually end up getting is a nice horizontal line for the derivative. Okay, now the start, it seems sort of easy. It's just trying to get your head around looking at it at the tangent lines. What happens to the tangent lines? Does it get infinitely steep? Is it negative? Is it positive? Then you kind of sketch out what it looks like. So the linear lines are easy. Have a go with B. What would the gradient graph look like for B? So have a look. And then you describe it to me once I pick you out. So I want you to have a look at B. And then we call you out and you tell me what would the line look like. All right, let's go with Suresh. What would the derivative graph for this one look like? Good. Gradient's negative. Do you know what the value is? 1, because it's 2 down and 2 across. So therefore, negative 2 over 2 gives you negative 1. Yes, so I know the gradient's negative. It's negative 1. Very good, because across them all, every single tangent line has a gradient of negative 1. So no matter which x values you choose, the m value is going to be negative 1. So it's a nice straight line on the bottom. In this case, it's negative 1. Let's go to part C now. Now, part C is slightly trickier, and I guess this is the one that you practice, and then you can start applying to the other functions as well. But let's have a look at this one. Just on the left side, so C, notice that at the very top, at the turning points, what do we know about the gradients at the turning point, Charlie? 0. Very good. Gradients, because the tangent line at the very top has to be horizontal. If you think about it, the only way to draw a tangent line that touches it has to be nice and horizontal. Therefore, gradients are 0 at x equals 1 and x equals negative 1. So on your graph, at 1 and negative 1, you should have a derivative graph of 0. So delta y, delta x should be sitting right at 0. Because remember, this represents the gradient axis now. So gradient has to be 0 exactly at negative 1 and 1. Now you've got to analyze now what happens when you go to the left side. So let's go with Erwin. Looking at this left side of the graph. At each point, what is the gradient? Is it positive? Is it negative? It's 0? What can we say? It's positive. Each of these points are all positive tangent lines. And then it reaches 0. So what we can see is positive is in the top half, which is up here. This is the top half. So my points should be in this direction. But notice that the gradients, the further I go down, it's a steeper line. The closer I get to the top, it gets closer to 0. So that means as I get closer to negative 1, it should actually go from infinitely large to 0. Then you look at after negative 1. What happens after negative 1? Let's go with Samar. What do we see? Very good. The gradient becomes negative. So from 0, it starts to go negative. And it gets infinitely large, but there's a little caveat here. What's the thing you have to be careful of between negative 1 and 1? What's something that you should be able to see there? What's something you have to be careful of? Let's go with Adonis. Do you see it? Between negative 1 and 1. So Samar's correct. He said that the gradient's going to be negative. It's all negative, and it's 0 there. But there's something between negative 1 and 1 that you should be careful of. What is it? Sorry? Not sure? Jason? There is definitely an x-intercept. Now, we can sort of see it, that there is this x-intercept. But one of the key things is you got to notice this was 0. Gradient 0 here, gradient 0 there. So if it goes from 0, think about your number line. 0, I go into the negative zone. So it should be increasing in negative. Negative is increasing really steeply. So it's really negative. But then how are you very negative and then end up at 0 again? Get me? So if you think about the number line, 0 is here, negative's that way. If I'm negative 100, how did I come back to 0 again? The only way that I came back to 0 is that somewhere along the lines, I had to start increasing my gradient. Get me? So that means that somewhere around here, I reach a maximum negative. Then it starts to grow positive or grow larger. It's a larger negative value. Get me? So instead of being negative 100, it might be negative 50 now. then negative 40, negative 30, negative 20, negative 10, and it gets closer to 0. So there has to be somewhere here, there is a maximum negative value. What does that mean for your graph? It means there must be some point it has to stop maximum negative value, and then it must return back to 0 to get back to 0 again. Otherwise, it will just keep going negatively. It goes all the way down. So then that point there was key. What is that point called? Anyone know? It's an inflection point. And that's the description I'm going to teach you in the next page. It's called concavity, where you look at concavity up, concave up versus concave down. There is a difference between this rate versus the next rate. Okay? So somewhere along here, there must be an inflection point. And it just means that it must be a very maximum negative. Okay? So there's a maximum negative before it comes back to positive. And then afterwards, that's the easy part. We can tell that the gradient's all positive from here, and it gets infinitely large, so that's why we can then do that. Which makes sense. This looks like a cubic graph, and if you derive a cubic graph, you get a quadratic. So hence, the pattern of a quadratic makes sense to describe what's happening in the cubic. But those key points are the ones that you want to pay attention to. So there must be an inflection point or the derivative, when the derivative equals 0 here, that's something you got to look out for. Okay? All right, team. So the first 3 examples I just did there, these 2 are straightforward. Straight lines are always easy. Derivative of a straight line gets you a constant, so that's why you get a nice horizontal line. This is where the practice really comes in for 9D. For those who are the first timers with derivative graphs, 9D, this is where you want to start practicing. And then the tricky ones is when you start having things like, asymptotes. What does it look like? There'll be different ones in your exercise 9D to try. I want you to have a go with the next 3, and then we're going to go through the answers to see if you get it correct. Okay? And there is a reason why this is called point of 0 gradient, whereas this one doesn't say it. There's a difference between these 2. Okay? Have a go, and then have a think of what F should also look like logically too. Okay? I'm going to pause the video. And then give you maybe 5 minutes to draw out your derivative graph. 5 minutes. Let's go. That's your DEF. These are, to me, still relatively easy. Find the ones in your textbook that has asymptotes involved. Those are good ones to challenge you. Or even the VCAR question I put on the very last page. That's a good one to try. Yeah. All right. Next one. Example 2, there is a common thing when it comes to sketching derivative graphs that you might get penalized in an exam to be careful of. So far, everything we've sketched, we include every single gradient. However, in a graph like this, there is a section where you do not include the gradient. Which part is the derivative or gradient of a tangent line undefined? Where is it undefined? Hands up if you know. 0, 0, 2. Very good. At 0, 2, where x equals 0, this spot here, m, is undefined. And the reasoning for this bit is you can see, well, they're both straight lines, and we've already done derivatives of straight lines. We know that that's a nice horizontal line with a gradient of, well, that's 1 across, 2 up, so it's a gradient of 2. Okay, so we know that this line will always have a gradient of positive 2. So it looks like this. If you were to sketch it, on the left side it should be a gradient of 2. But then what's interesting is that as soon as you pass the 0 point, and you go to x equals 1, x equals 2, x equals 3, the gradient now is negative 2. Every single point has a gradient of negative 2. So that means on this side, your gradient now is negative 2. So why is it undefined at this specific point? Because at x equals 0, right here, is the derivative going to be 2? Or is the derivative going to be negative 2? And that's what we don't know. Okay, so if you use limits, using first principles going limits, as you approach x equals 0, is the gradient meant to be 2? So as you're approaching x equals 0, Is the gradient meant to be 2? Or is the gradient meant to be -2? And because we can't determine it, in the exam, they'll be checking that you put open circles to show that it's undefined there. So you should have open circles at x equals 0. And that's just a typical, simple idea. What's a little note that you can write down for people who are first timers with derivative graphs? Any sharp points or endpoints have undefined gradients.
I feel like we're going to need like some niche.
Okay, so any sharp points, if they're smooth and they're continuous curves, they will have a derivative. It's only at sharp points and endpoints. Okay, so that's if you didn't know that. Now flip over the page. This one is a bit more information for you on inflection points. Most SPES students already know this. This is more just FYI. It is part of your textbook, so I just thought I'd go through the notes with you. Fill this in. Whoops. I'll just leave it there, actually. I should have deleted them, but it's okay. There's two terms that you may or may not have heard before, which I think for the mainstream students wouldn't have. Concave upwards versus concave downwards. This is the definition for an inflection point. So you guys traditionally know an inflection point looks something like this. Here's your cubic graph. And then you'd say, yeah, it goes from positive to 0 gradient, or not 0 gradient, or so 0 gradient, and then it goes positive again, right? The inflection point, how do you know, or what's the definition of an inflection point? It's the change, it's the moment that it changes from concave upward to concave downwards, or vice versa. Okay? So the question is, what is concave upwards and what's concave downwards? And when I describe it to students at the start, they're kind of like, oh yeah, I get it. And they look at this graph, they're like, this is concave upwards. This is concave upwards. And then they're like, but why is this concave upwards? Because in their mind, they're thinking of it's when the graph looks like it's going up, right? So the question is, why is this concave upwards? Because it looks like it's going down. The logic to it is concave upwards is talking about the gradient in terms of value. You see, here, if I look at this one, is my gradient increasing? At this point, it's a very steep negative gradient. This is a less steep gradient, but it's also negative. So in essence, I can say this is like negative 100 gradient. This is negative 50 gradient. Technically, that is increasing. It went from negative 100 to negative 50, negative 50 to negative 20. That is increasing. Because the gradient's increasing, if you think about the number line, I'm going from negative 100 to negative 50 to then 0 to then positive. That's called, if you're increasing the gradient, it's called concave upwards. Okay, that's why all of these are concave upwards. Goes from negative 0 positive. It goes from negative 0 positive, goes very steep negative to less steep negative. It's increasing in gradient, the value. Okay, so if you think in that sense, concave upwards means when the derivative or the gradient or the slope is increasing. Think about the value. Okay? So that's what concave upwards means. Concave downwards is talking about when the gradient decreases, going from positive to super negative. Yeah, so if you're going from positive to negative, you can see here, positive gradient, 0, and it gets really negative. This is positive gradient, 0, goes more negative. This one, yes, it's negative, but you're going from small negative to larger negative, so you're decreasing. It's getting more negative. That's called concave downwards. So when you look at the inflection point of a typical x cubed graph, you can see where that happens. This is positive, 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 but it's getting smaller and smaller and smaller until it gets to 0. So if you think about the numbers, this is decreasing in gradient. You know what I mean? So this is really high positive to really flat. So this is now concave downwards. Versus this one, it goes from 0 and it's increasing. See that section? Because it's increasing in gradient. And I know this is still positive, 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 but one's decreasing in value, one is increasing in value. So we call this section concave upwards. This section is concave downwards. The moment it changes from concave downwards to concave upwards, that's where your inflection point is. Okay, so that's the definition. In a nutshell, if you want to find it, and I think this is where the special students come in, they do the double derivatives. We don't often do double derivatives in methods. It's more common in special, but that's something that you can apply too. So it means that you're looking at when the rate of change of the gradient, which is the derivative of the derivative, when it equals to 0, that tells you whether there's going to be a change, whether the gradient of the rate of change is going to be flat or positive or goes into negative. So here's your description, fill it in. When your derivative, you find the derivative of a function, you are finding the gradient. And to quickly figure out if there's concave upwards or concave downwards, you can actually do the second derivative. It just means derive it twice. Okay? Derive it twice. If you derive it twice and it is a positive answer, then we will say it is concave upwards because it's saying that the gradient is increasing. If you do the second derivative and it is negative, then it means the function is concave downwards is because the gradient is decreasing. Okay? And so therefore in this example, which I've left it there from last year when I was explaining it, you find the derivative of x cubed minus 6x squared plus 11x minus 6. That's the first derivative, so that tells you the gradient graph. But from the gradient graph, if you derive it twice, now you're looking at the rate of change of your gradient. So therefore 6x minus 12. We know that inflection points, there has to be a change. If there's going to be a change, there must be a 0 somewhere. So if we let it equal to 0, we find out it's at x equals 2. This is what it looks like. Here's your graph. Here's your derivative graph. And in your gradients, you can see the derivative graph changes right at the maximum negative. So it goes negative, 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 and then it increases in gradient to become 0, or decrease in gradient to become 0, and then increases from there onwards. So that one is decreasing, increasing, and then this one is increasing from there. You see that? So you're going from very negative, and you're increasing, so this is a concave upwards scenario. Yeah? And that's why we know there's an inflection point at x equals to 2. So the moment that the derivative, double derivative, changes from negative to positive or vice versa, that is the inflection point. Okay, so copy those notes down. One is the function. One is the derivative graph. And it does get tricky to try to apply that skill and be able to read the gradient. Because you're trying to move away from understanding it as look at y values, and you're trying to look at the gradient, and now you're looking at the rate of the gradient. And I can understand that's tricky. Okay, that's why I'm saying it's probably more familiar for special students. For us, as method students, usually we don't do a lot of the concavity concept or double derivatives. Okay, but in case you wanted to use it, double derivatives, yeah, those are some notes for you to fill in. Otherwise, on the very last page, if you flip over, that's an example of VCA question. Have a go with that and see if you sketch it correctly with all the key markers, and I'll show the solutions afterwards, see if you've actually got the concept. And that's exercise 9D. So 9D is the skill to be able to look at a function, determine what the derivative graph should look like, and what are the key points where it is undefined. Okay, so that's what you want to be able to do. All right, team, I'm going to stop the video there. is